Hello Dosto, welcome to Apni Kaksha. I'm so glad you're here, because today we're about to uncover something truly fascinating that surrounds us every single day. Today we're diving into a topic that's invisible but everywhere: radioactivity. It's a force that quietly shapes our world, even though we rarely notice it. Imagine atoms, tiny building blocks of everything around us, from the air we breathe to the food we eat. Some atoms are unstable, packed with extra energy that makes them restless and eager to change. To become stable, these atoms release energy as invisible rays or particles. That's what we call radioactivity, a natural process happening all the time. It's happening all around us, even in things like bananas, which contain a tiny bit of radioactive potassium-40. Even the soil and air have traces of it. You can't see or feel radioactivity, just like you can't see Wi-Fi or mobile signals, but it's real and powerful, silently working in the background. While movies make it seem scary, radioactivity isn't just about danger. It's a tool that's changed our world. It helps generate electricity for millions of homes, treat cancer with advanced therapies, and even helps us understand the age of ancient objects. The key is understanding how it works and how to use it safely, so we can benefit from its power without harm. Today, we'll break down radioactivity into simple concepts, explore its discovery, types, uses, and risks, and see how it's part of our daily lives. Ready to explore the hidden world inside the atom? There's so much to discover. We'll see how scientists uncovered these mysteries through experiments and curiosity, and how radioactivity shapes our lives in ways you might not expect. Grab your notebook and let's start this amazing science journey together. Let's go. Our story starts in 1896 with Henri Becquerel, a French scientist curious about glowing materials. He experimented with uranium salts, expecting sunlight to make them emit rays. But when cloudy weather forced him to store his materials in a dark drawer, he developed the photographic plate anyway, and found a strong image. The uranium had emitted powerful rays without any sunlight. This was something new, energy coming from inside the atom itself. Becquerel had discovered a new kind of radiation, radioactivity. His accidental find proved atoms weren't unchangeable. Some could release energy spontaneously. This discovery opened the door to a new field in physics. Soon, other scientists would build on his work and unlock even more secrets of the atom. Inspired by Becquerel, Marie Curie and her husband Pierre set out to study these mysterious rays. Marie discovered that radioactivity depended on the amount of uranium, not its chemical form, proving it was an atomic property. She found thorium was also radioactive, then noticed pitchblende ore was even more active than pure uranium. This led the Curies to discover two new elements, polonium and radium, both far more radioactive than uranium. Their work, done in tough conditions, changed science forever. Radium glowed faintly, showing the immense energy inside atoms. For these discoveries, the Curies and Becquerel won the Nobel Prize in Physics in 1903. Marie later won another Nobel in chemistry for isolating radium. She coined the term radioactivity and proved it was a property of atoms, laying the foundation for nuclear science. Their legacy continues to shape medicine, energy, and technology today. What exactly are the mysterious rays that come from radioactive materials? These invisible forms of radiation have fascinated and puzzled scientists for over a century. In the early 1900s, Ernest Rutherford discovered there are three main types: alpha, beta, and gamma rays, each with their own unique characteristics. By passing these rays through a magnetic field, Rutherford observed them split into three paths. One bent slightly, which he called alpha. One bent much more, which he named beta. And one continued straight ahead, which he identified as gamma. Alpha particles are heavy and carry a positive charge, making them the largest and slowest of the three. Because of their size, alpha particles can be stopped easily. Even a sheet of paper or the outer layer of your skin is enough to block them. Beta particles, on the other hand, are much lighter and are actually fast-moving, negatively charged electrons. They can travel further than alpha particles, but are still stopped by materials like aluminum sheets or a block of wood. Gamma rays are different. They're not particles at all, but powerful high-energy waves, similar to X-rays, but even more energetic and penetrating. To protect against gamma rays, you need thick barriers like lead or concrete, since they can pass through most other materials. Alpha radiation is only dangerous if inhaled or swallowed, while beta radiation can burn or damage skin on contact, and gamma rays can penetrate deep into the body, potentially harming internal organs and tissues. Understanding these three types of radiation is crucial for using radioactive materials safely and for protecting ourselves from their harmful effects. Each type has its own set of properties, uses, and risks, making them important to distinguish in science and medicine. Rutherford's discovery was a major breakthrough, opening the door to our modern understanding of atomic energy and nuclear science. Let's take a closer look at the power and penetration of alpha, beta, and gamma radiation and see how their unique properties affect the way we handle and protect ourselves from them. Alpha particles are big and slow. They lose energy quickly and can't travel far. Even a simple sheet of paper is enough to block them, making them the least penetrating of the three. Beta particles are smaller and faster, so they travel further and can penetrate the outer layer of skin. However, a thin sheet of aluminum or plastic is usually enough to stop them, offering effective protection. Gamma rays are different. They're pure energy, with no mass or charge, and they move at the speed of light. Gamma rays travel great distances and penetrate deeply into most materials, so only thick barriers of lead or concrete can effectively protect us from their powerful energy. Now, let's talk about ionizing power. Alpha particles, though easily stopped, cause intense damage in a very short distance. They're highly ionizing and can do a lot of harm if they get inside the body. Beta particles are less ionizing than alpha particles, but they can travel further and penetrate deeper, making them more of a concern for external exposure. Gamma rays are the least ionizing, but they're the most penetrating, able to pass through the human body and even thick walls. So, alpha radiation is high in ionization, but low in penetration, while gamma is the opposite, low ionization, high penetration. This balance between ionizing power and penetration is key to understanding both the risks and the practical uses of radiation in science, medicine, and industry. Knowing these differences helps us choose the right protection and safety measures for each type of radiation. It's all about matching the shield to the type of radiation, so we can work safely and efficiently. By understanding these principles, we can stay safe, make smart choices, and use radioactivity wisely in our daily lives and scientific work. Radioactivity isn't just about bombs or power plants, it's part of everyday life. In medicine, radioactive tracers help doctors diagnose diseases and target cancer with radiotherapy. Gamma rays can destroy tumors while sparing healthy tissue. Smoke detectors in your home use a tiny amount of americium-241, a radioactive element, to sense smoke and keep you safe. Food irradiation uses gamma rays to kill bacteria and extend shelf life, making food safer without making it radioactive. Radiation sterilizes medical equipment, ensuring safety in hospitals. Nuclear power plants use controlled radioactivity to generate electricity for millions. These uses show how radioactivity, when managed well, benefits society. It's a hidden force behind many modern conveniences. Radioactivity is more helpful than you might think. Radioactivity is powerful, but it must be handled with care. Its ability to damage cells makes it useful for cancer treatment, but also dangerous to healthy tissue. High doses in a short time can cause radiation sickness or even death, as seen in nuclear accidents. Long-term low-level exposure increases cancer risk by damaging DNA. Workers in nuclear fields follow strict safety rules and monitor their exposure. Alpha particles are most dangerous if inhaled or swallowed, causing intense internal damage. Beta and gamma rays can harm from outside the body, penetrating skin and organs. Understanding these risks is crucial for safe use. Respecting radioactivity's power keeps us safe. Knowledge and caution are our best protection. How do we stay safe around radiation? 3 key principles: time, distance, and shielding, summed up as ALARA, as low as reasonably achievable. Minimize time near sources to reduce exposure. Increase distance. The farther you are, the less radiation reaches you, thanks to the inverse square law. Use shielding paper for alpha, aluminum for beta, thick lead, or concrete for gamma. Workers use tools and barriers to keep safe. Hospitals and power plants are designed with these principles in mind. Following these rules protects both workers and the public. Simple steps, big impact. That's how we harness radioactivity safely. Let's bust some myths. Not all radioactive things glow. Most don't glow at all. Some of the world's most radioactive places are natural, like beaches in Brazil or hot springs in Iran. Nuclear power plants can't explode like atomic bombs. Their fuel isn't pure enough. Accidents can release radiation but not cause nuclear explosions. Fun fact, you're slightly radioactive. Foods like bananas and potatoes contain potassium-40, and your body has carbon-14. This natural radioactivity is harmless and part of life. Radioactivity isn't alien. It's a natural part of our world. Understanding it helps us use it wisely and safely.